seconds. On top of that, intermediate servers have to wait for some distribution of the backend nodes to finish execution before it can send any reply back to the user. But this distribution most of the time contains all or nearly all of those servers. So to optimize user experience, we need to minimize the tail latency of individual leaf nodes. Interested audience, I can point you to the tail at scale paper by the Jeff team dating back to the early 2000s, and you can check the accompanying talk for the importance of the tail latency. Coming back to the question why we have this efficiency gap, why one of these backend servers can fall behind. It is evident that achieving low tail latency at microsecond scale is hard. We identify the issue is the conventional operating systems are not very good at scheduling this type of workloads. First of all, they have very high overheads, and secondly, they react in millisecond, and if something goes wrong, it means we need to take a bunch of milliseconds to react. The conventional wisdom here is to build specialized systems that bypass the operating system and completely expose the hardware to the user space. By doing so, such systems can use polling instead of the interrupts, they can run the request to the completion, they can even delegate load balancing to the hardware. In such systems, there is usually a common pattern. They have a queue per core, and packets coming in are hashed by the NIC using the receive side scaling, which I will refer as receive side scaling. And NIC using the RSS will direct this packet to the empty queue here. We call this type of architecture and scheduling distributed first come first serve, and it is used by systems like the DPDK, X, TAS, Snap, ERPC. For your reference, DPDK is the main enabler here, and most of the systems are in one way or another building on top of that. And Snap is the production system used by the Google. They have actually 2019 SOSP paper about this. ERPC is the best system with the performance according to my knowledge. One common thing is that all of these systems requires hardware support in one way or another. For example, they rely on the flow steering to redirect matching packets to a specific receive queues. They use RSS reconfiguration to play with the core to queue mapping by doing the modification of the RSS key or redirection tables. Sometimes they use the transaction side DMA from the app memory, or they even utilize the remote DMA, which is also known as an RDMA, to efficiently to transmit and receive the packets. Sometimes they use the deep receive queues to prevent host-side packet drops, or multi-packet receive queues to handle receiving multiple packets with a single descriptor. But bottom line here is that all of these mentioned systems mainly assume that you control the NIC using the hardware support. But the cloud is very different. Traditionally, on premises, people have been using these bare metal servers with the NICs where they have the full control of the hardware. And as they move to the private cloud, virtualization came to the hardware, and you can partition the hardware into multiple functions. For NIC, for example, you can divide up to 128. I think even with the higher ends, you can get up to 10 to 24 virtual functions within a single NIC. It is very similar if you are familiar with the multi-instance GPU case with the new A100 or H100 architectures. So here, bottom line is that you partition the hardware into virtual units, and you give control of those units via the device path through to the VMs. But when you rent a VM in the cloud, the story is totally different. Here what you see is the network virtualization, at least for the NICs. If you ask the question, why do we need a network virtualization here, I would say many reasons. One of the main reasons here is that these companies are operating with multiple generation and multiple vendors of the NICs. They have a large fleet, they need to support a uniform virtual NIC abstraction to their clients. And also they are running multiple services here, like the billing, security, observability, and so on. So these virtual NICs do not expose key features like I mentioned in the previous slide. They don't have any flow steering available, they don't have configurable RSS, and they have very small queue depths. So what should be the requirements for the kernel bypass in the cloud. I would say the first requirement should be the system needs to be NIC agnostic. The stack should not depend on any NIC features other than those available in the vast majority of the public cloud. Secondly, it should support diverse application and execution models. It doesn't need to make tough decisions about the programmability, like picking up a library operating system or like abruptly changing the trading models. Third, it should be low latency. We shouldn't compromise the low latency by giving off the hardware features. And we also define two non-goals here. First, we need to be able to support ultra high bandwidth VMs, which is like 25 Gbps or 40 Gbps, even 100 Gbps NICs that are available in the public cloud nowadays. And it should also be compatible with the unmodified applications. What I mean by the unmodified application here is that we need to invest minimal effort to get the application working with this stack. So we define the least common denominator, which we'll call shortly LCD model here. The common set of features that are available in the all modern kernel bypass clouds like AWS, Microsoft Azure, and GCP. We did a survey across the VM instance types that they are operating and bring up with this paper, with this table. We defined that the Ethernet frames should be a standard I/O interface instead of RDMA verbs and so on, because it is not generally available across the instance type. Also, number of the receive and transfer queues should be equal to the number of the CPU cores, as well as per receive and transfer queue there should be at max 256 descriptors. If you ask why these numbers, I would say that cloud providers virtualize the NIC queues and run among the tenants, so each tenant gets a limited amount of these resources. So these are the maximum numbers that we can support. This precludes designs like the ERPC, for example, that create very large receive queues to avoid host site congestion and packet drops. The LCD NIC requires posting and polling one descriptor per packet. Descriptor coalescing optimization such as batching multiple packets per descriptors will be unavailable with this design. So how we can design system given this virtual NIC model? We say that the new user space stack should adopt a sidecar approach. Here, sidecar should own the NIC. With this layer of indirection, multiple processes and threads can use the same NIC. Even let's say you have applications using the multiple languages, they can talk to this sidecar to reach the network. And also, given we have this opaque RSS, which means we do not have any key reconfiguration and access to the redirection tables, we cannot rely on the RSS. So we propose RSS ---- algorithm, which I will talk more about in the upcoming slides. Given this design requirement, we implement a system called Machnet and call it fast networking for everyone. Here, Machnet is a user space stack designed for this LCD model. As I mentioned, it uses a sidecar model that owns the NIC and multiplexes across application threads. It scales across cores with a shared nothing architecture, and it implements our RSS ---- algorithm, which is a packet spraying scheme that distributes flows evenly without hardware steering. I will motivate why do we need this packet spraying and its performance implications in the upcoming slides. We also implement here highly optimized shared memory channels to become constrained in the shared nothing architecture, which takes into account all the cache architecture of the CPU, L1, L2, and L3, and try to minimize this inter-core communication. Again, coming back to the RSS ---- I would like to describe a scenario where we are trying to scale the Machnet. As I mentioned, it is shared nothing architecture, so one thing can directly come to your mind is that when you want to saturate the bandwidth and scale, you can just horizontally scale it by increasing the number of the cores. By doing so, you will avoid the cost of the synchronization because there is no coupling between those cores. In this scenario, each application thread will be bound to a specific engine 1 and engine 2, let's say. As you do not have the receive side scaling and no hardware support, let's say a packet comes, and opaque RSS here can mess up with the flow to engine map, and this packet which is supposed for the engine 1 can end up in the engine 2. So Traditionally, the system that I mentioned, the Snap, which is Google's production system, used the NIC's flow steering hardware to map flow to the engine so that this guy will come to the engine 1. But we do not have it. There is another system called TCP as a service, which is a research prototype in Eurosys 2019. They propose to use this problem only in the software by sending to all the application threads, which is not that efficient performance-wise and will not scale to the large number of threads. What we do here is that at the connection initiation time, we repeatedly try to establish connection using different source and destination port and IPs and reverse engineer the RSS key. By doing so, we keep the hashes in a hash table for the desired receive queues in each engine. So we will exactly know how to route the coming packet. So we have more features also in the Machnet. For the brevity of this talk, I'll just mention them and not dive deeper to them. We have the port mapping to reduce the number of the packets sprayed. We have connection-oriented transport protocol, which is reliable transport protocol, very similar to the TCP. We also implement blocking receive to save CPU cycles on the application side. We package it as a container, Docker container, so it is very easy to distribute. You don't need to have any DPDK-based experience. You can directly get it and work, even let's say you do not have that much low-level networking expertise. And also we export C++, C, Go, Rust, Java bindings, JavaScript bindings, so that the people can easily adopt this project for their networking needs. We evaluate Machnet in different cloud providers, I would say in all the cloud providers which are available, and we consistently see lower latencies, especially for the Microsoft Azure. For 64-byte messages, round trip latency is under 50 microseconds for 64 bytes. And we consistently see lower latencies for the other providers. We evaluate it and compare with 3 main systems. Here Linux TCP is the universally available system that can run from the embedded system to the most high-end servers. ERPC, as I mentioned, is the best performance system, which is non-LCD, and TCP as a service. So we port the faster key value store of the Microsoft and evaluate, and as you can see, it is well under the 50 microseconds and can scale to I think around 1 million. For the CPU scalability horizontally, you can see that as we scale it horizontally, we will get higher throughput and it will scale linearly. We also compare it with the non-LCD stack ERPC, and we see that for the 99 percentile latency, it is just 3 microseconds worse than the ERPC without using any of the fancy hardware features, just being a software-only solution. Also, RSS establish connection quickly. Here, these lines correspond to application-to-application scenario. 1-to-1 means we have one application talking to another application. 4-to-4 means 4 applications from one VM tries to talk to 4 applications on the other VM, and 8-to-8, which is very extreme case that no one will deploy such a thing. And we see that it is always under 1 millisecond for 1-to-1 and under 3 microseconds for the 8-to-8. So we have a lot of other stuff in the paper. We have ported the etcd, which is working on the Raft consensus protocol, very network-heavy application. We also have ported the Nginx HTTP server and the WRK load measuring tool. We also have more throughput tests, and more interestingly, we have blocking tail latency under 40 microseconds. I would point the interested audience to check out our paper. So the conclusion is that building a microsecond scale networking stack for the public cloud is challenging but doable. There are a lot of the hardware features, but we can play with the software to achieve better performance and be compatible with all the major clouds. You can check the code in the GitHub under the Microsoft organization. Given this, can we say that we have solved the kernel bypass networking in the cloud? Does this solve the microsecond scale performance? I would say not quite. I remember one time I was doing this simple experiment where I was sending the Machnet 64-byte messages again in one cloud provider, I don't want to name it. And suddenly I saw that the latencies are very bad. They are going above the 10 milliseconds. I thought it might be a bug, so it was investigating. But when I investigated further, we pinpointed that the bottleneck is not anything software related. It's actually the cloud provider's problem, and it's related to the VM scheduling. So I delved into a new area and checked how the VMs are scheduled. So VM schedules are actually complicatedly scheduled. I'll give you some background here. In the VMs, actually, when you run your application within the VM, there are two scheduling layers. First of all, your application have some threads, and your guest operating system within the VM will schedule those threads on top of the virtual CPUs. What happens outside the VM is that you have the hypervisor which picks up those virtual CPUs and again schedules them on top of some physical CPUs. Everything is good here until every virtual CPU has a dedicated physical CPU. But that is not the reality. All the cloud providers, best of my knowledge, oversubscribe in one way or another. Let's say if you are using a spot VM, it's highly likely that you are using some oversubscribed VM, which means you have more virtual CPUs given the bare metal than the available physical CPUs. And this creates a hidden contention. So there are a lot of classic problems here, namely lock waiter and holder preemption, priority inversion, which date back to early 2010s. There are a lot of classical works in the academia done. But I want to talk about some different problem that we notice today. So for example, there is this system called UFO, which claims to be one of the state-of-the-art, actually published in 2024. They are doing a simple trick here. They are trying to dynamically adjust the vCPU count. If I explain in the layman's terms, it is happening like this. Hypervisor has a communication channel with the guest operating system, and when it adjusts the number of the cores for the guest, it communicates it back to the guest. And guest kernel, in response to this, will either hot unplug or plug the virtual CPUs and try to match the number of the virtual CPUs to the physical CPUs so that basically there is no oversubscription. But by doing so, you do not solve the problem. You just hide the problem under the carpet. And now there will be a bad contention within the VM. To showcase this, we are running this simple experiment. We pick up the silo, which is an in-memory database, microsecond-scale, widely used in most of the academic papers, and running the TPCC benchmark, which is a standard benchmarking tool, and we configure it for the low load around 20K TPS, which is 20% of the available hardware. Here I have 4 cores designed for these VMs. Native represents the case where you have no oversubscription, and all the rest are the oversubscribed cases. UFO works as I described, and vanilla is as the name suggests. It is just 8 virtual CPU on top of 4 physical CPU. As you can see, there is 30 times gap, and more badly, it is well above the millisecond scale rate. So, if you think more about this problem, as I mentioned, it is just hiding problem in another layer of the abstraction. How the guest scheduler work is that we have many threads within the guest scheduler now, and they are bound by the guest scheduler's time slice, and it will make situation more tough there. And the provider will not have any control over the guest scheduler because customer can use whatever he likes. They can use, I don't know, even Microsoft Windows proprietary operating system or like some of their own kernels. So what should be the problem? What should be the solution for this? We derive the following requirements. First of all, we need to avoid nested scheduling contention, which I labeled as hiding the problem under the carpet. Secondly, we need to degrade the performance gracefully under oversubscription. Let's say if you have an oversubscription ratio of 2, your performance needs to be worth 2x, not 30x. And we need to achieve high efficiency and keep all the cores from the hypervisor perspective utilized. So we propose a simple solution here, which we call host-level processor sharing. It dates back, original papers dates back to like very early times, 70s, 80s even. Instead of waiting for the guest, the host gives each VM's virtual CPU microsecond time slice. Here the challenge is that how we can implement these microsecond scale time slices, because VMs are different beasts. Even here, context switch can have a lot of complication, overheads, both security-wise and performance-wise. But this way, every virtual CPU will make forward progress, and tail latency only will grow linearly without oversubscription ratio. Coming back to the requirements, we will see that this will minimize the delays, and we prove mathematically in our paper that the tail latency that you can suffer is capped by the factor of the oversubscription you will have here. To achieve the high efficiency, we will have dynamic time slice adjustment, which I'll talk more about it. So we come to the second system that we designed. We call it Rorke, which is a black box microsecond scale VM scheduler. It uses per VM run queues and microsecond scale preemption. Here time slice length is adaptive. Why this is adaptive? It would motivate to talk about some work from the early 2010s where they noticed that if you are trying to preempt tasks very fast, they can have very bad effects on the performance. Like, let's say if your application is memory heavy and it brings some stuff to fill the L1, L2, and L3, and you prematurely preempt this, and next time it will just spend its slice to again loading those stuff to the caches. So our strategy here is that by monitoring the low-level performance metrics, we can create a model of the workload by just looking at those numbers. These are the IPC, L1, L2, L3 cache hit and miss ratios and other stuff that we try to model and infer what type, like popular way, let's say learn what type of an application running there. We implement this system on top of the Linux SCDXT framework, which is also another interesting framework gaining more popularity and supported by the Meta as an open source project, which is basically they implement and upstream the new class of Linux scheduler, exporting some callbacks as an eBPF. We did also some optimizations here. We patched the kernel so that to have microsecond scale preemption, how we can handle the timers. We did some optimizations there, which I don't want to talk here for the sake of the time, but feel free to ask about them later to me. And we evaluate our system against three setup. As I say, native is the scenario where there's no oversubscription. Vanilla is regular oversubscription, and the UFO is state of the art. So we use the silo parsec and Machnet, which I mentioned previously. As you can see in this graph, we always keep up the promise that we are under 1 millisecond, which we operate in the microsecond scale very close to the native. And actually it is 11 times lower latency than the UFO and 30 times better than the vanilla oversubscription. And also we evaluate patch workloads from the parsec suite. It's very common suite in the academia that people use for evaluating the CPU-heavy workloads. It consists of, for example, Black-Scholes model. If you are familiar with the finance industry, it has some other simulation tools. We observe that most of the time our throughput loss stays under 5%, which is very acceptable. You bring your tail latency from millisecond scale to microsecond scale by just losing 5% of the throughput, which is not that important nowadays. More importantly, I come back to the point where I started. I discovered this problem while I was experimenting with the kernel bypass networking, and I here confirm that whatever happens, Rorke will make this kernel bypass networking to work in the microsecond scale, and it will even drop the latency by 76 times compared to the state of the art. So we have more in the paper. We have more scalability experiments. We have more dynamic experiments where we change the number of the virtual CPUs over the time and see how the diurnal patterns can affect the VM scheduling. We also have the RuxDB and PostgreSQL evaluations, which are two famous. One of them is the key value store by the Meta, and the other is widely used database management system. So to wrap up, together Machnet and Rorke attack the two big bottlenecks. Machnet fixes the cloud networking under the virtual NIC constraints, and Rorke fixes the virtual CPU scheduling under oversubscription. Both of them preserve portability and work as a black box solutions, so they are deployable in the real public clouds even today. We address this challenge. There are also still many more opportunities, like what about the GPUs? Now we solved the problem with the NICs, we solved the problem with oversubscription, and how we can do better GPU virtualization and support the emerging agentic applications or like training, inference, that type of stuff. And also how we can allocate the resource at microsecond scales. Most of the resources nowadays are allocated in the millisecond scale or like even second scales. And some companies are using some ML-based tooling for high-level job management. But I think it would be more efficient to utilize the sources in the microsecond scale. For example, for workloads like the key value stores, or like a technology called the virtual radio area networks. And there are still some other type of workflows can benefit from this type of stuff. And also, what about the storage virtualization? You know, most of the storage nowadays are virtualized. And yeah, another interesting question is that where does the machine learning fit in here? How we can benefit from the machine learning for some of these policy adjustments. I am mainly nowadays focused on the GPU virtualization aspect of the things and trying to do a little bit with the ML to fit in, especially for the adaptive time slice setting. Happy to take questions and discuss more with you. Thank you very much again for hosting me today, and yeah. You can get the Machnet if you are interested about the code. It's on the Microsoft, under the Microsoft repository. The other system is not open source yet because of some anonymization reasons for submission. If you ask me, I can point you to like some personal fork, private fork. Yeah, go ahead, please.